Hello, everyone. Thanks so much to the Voice Foundation for this very nice invitation. It is an honor to me and a pleasure today to be talking about optimizing vocal efficiency and economy to combat vocal fatigue. The title of this presentation includes several concepts that we need to define before to move forward. First of all, it says optimizing. Optimizing what? Vocal efficiency and vocal economy. What for? To combat vocal fatigue. We will be defining glottal efficiency for this presentation, which is defined as the acoustic power, which is the output, divided by the aerodynamic power, which is the input. And the aerodynamic power is the subglottic pressure multiplied by the airflow rate. So an efficient voice is always associated to a good conversion from aerodynamic to acoustic energy. But unfortunately, this measure ignores the possible damage on vocal fold tissues due to the impact stress or vocal fold collision. For that reason, we need to take into account the concept of vocal economy, which is the acoustic power divided by the mechanical load, meaning impact stress, vocal fold impact stress. According to Laukkanen, the vocal economy is the price of decibels that we need to pay when we need to increase the acoustic power. And what's the price? What's the price that we need to pay? It's an increment of the vocal fold impact stress or vocal fold collision. According to Berry et al. In 2001, maximum vocal economy is defined as the maximum relationship between the vocal output in decibel and the interglottic impact stress in kilopascal. When we have a maximum vocal economy, we have a lower risk of phonotrauma caused by the impact stress or vocal fold collision. Unfortunately, a universally accepted definition of vocal fatigue is currently lacking. But a common definition for this concept is a set of self-perceived vocal symptoms as well as physiologic negative adaptations following an extensive vocalizing. For this presentation, I will base all definition on the Dr. Hunter article just published in 2020. And author defined several concepts. The first one is the vocal demand. And vocal demand is defined as the vocal requirement for a given communication scenario. Author then defined what is vocal demand response. And they say that the vocal demand response is the way voice is produced in response to the perception of a communication scenario. Vocal effort is the perceived exertion of a vocalist to a perceived communication scenario, which is the vocal demand. And finally, vocal fatigue is a quantifiable decline in function, both performance or perceptual, that influences vocal task performance and is individual specific. Therefore, the goal of voice training and voice therapy, given a vocal demand, is to find an optimal vocal demand response, the way voice is produced, and also an optimal vocal effort, the perceived exertion. In order to accomplish this, we could reduce the external vocal demand, but unfortunately, this is not always possible, or this is not always totally possible. So we need also to reduce the vocal effort and to balance the vocal response in order to avoid or eliminate vocal fatigue. It is very important to keep in mind that optimization of vocal response may then occur even when the vocal demand does not change. A possible way to get an optimal vocal effort and to balance the vocal response is by improving the vocal economy, mentioned just a few minutes ago, through a direct voice therapy, in order to get an optimal biomechanical and aerodynamic setups. An optimal biomechanical and aerodynamic setups include to control several variables such as subglottic pressures, vocal fold adduction, tensile stress, aerodynamic stress, supraglottic activity, vocal tract configuration, airflow rate, vocal fold length, collision stress, shear stress, and breathing pattern, among others. These variables are dependent on the interaction between breathing, phonation, and resonance. These three main subsystems involved in voice production should be treated always in an integrated manner, meaning using a physiologic approach of voice therapy. And I recommend to use as a tools semi-occluded vocal tract exercises, SOVTE. SOVTE are voice training and therapy exercises involving both lengthening and occlusion of the vocal tract. In this slide, we can observe some examples of SOVTE. The nonlinear filter system is important to better understand the effect of SOVTE. First of all, we have the source, which is the vocal fold oscillation, vibration, which creates an input which goes into the filter, the vocal tract, and finally we have an output. However, we have a new component, the feedback, the first feedback, which is from the filter, from the vocal tract to the vocal source. But there is also another feedback, which is not still supported by evidence, but we can observe this interaction between the filter and the breathing function in clinic. So there is a new interaction between the filter and the breathing function, meaning that when we change the vocal tract configuration, for example, from an open vocal tract to a semi-occluded vocal tract, we will activate the breathing function in a different way. We could say, therefore, that there is a greater source-filter interaction, but not only a source-filter interaction, but also a breathing filter interaction, and finally, also a source-breathing interaction. But why SOVTE are a good option to improve biomechanical and aerodynamic setups? Well, SOVTE not only promote an appropriate biomechanical and aerodynamic setups, but modifying specific voice parameters, but also provide an important source of sensory stimulation necessary to change the voice production pattern. We are talking about here motor learning, which is probably the most important part of voice therapy and voice training. Regarding vocal economy and SOVTE, in 2007, Dr. Titte and Dr. Laukkanen suggested that by optimizing the vibratory sensation in the face that are attributed to increased intraoral acoustic pressure, phonation into a tube may assist at training in finding an optimal glottal and epilaryngeal settings for the greatest vocal economy. Also regarding the vocal economy and SOVTE, in a study performed in 2019, which title is Variation in Vocal Economy After Different SOVTE in Subjects with Normal Voice and Dysphonia, the purpose of our study was to observe the possible differential effect of 8 SOVTE on vocal economy measured by the quasi-output cost ratio. This was our main outcome, the quasi-output cost ratio. Significant differences were found when comparing pre and post stages regardless of the vocal condition, normal voice or dysphonia, or the specific SOVTE used. In general, there was an increment of the quasi-output cost ratio, which is a measure of vocal economy, after SOVTE. When individually comparing the effect of each SOVTE, only tube in water, WRT, shows significant differences between pre and post conditions. So the quasi-output cost ratio, which is a measure of vocal economy, were higher after SOVTE, specifically WRT, water-resistant therapy. Tube phonation and WRT are two commonly used SOVTE for voice training and voice therapy. And these are very useful SOVTE because they increase the inertive reactance because of the tube, and also there is an increased flow resistance in different degrees, of course. We will be talking about this later. But very important, they provide a sensory stimulation. They provide a very nice source of sensory stimulation, which is a very important feature for motor learning. In order to obtain the best vocal demand response for each patient, we need, of course, to customize voice therapy by knowing and controlling several biomechanical and aerodynamic features during the use of SOVTE. So let's now take a look on some changes caused by SOVTE that we need to control in order to improve the vocal demand response in patients with vocal complaints. This is very important and we need to keep it always in mind. SOVTE are not the treatment by themselves, but they are nice tools to accomplish a proper result. The treatment is the effect produced by SOVTE and the way that we use them and teach phonatory tasks producing a good sensory input. So recall that the good sensory input is probably one of the most important aspects to build a proper motor learning. SOVTE are known for producing changes in air pressure related variables. When we produce a tube phonation or tube phonation into the water or any other SOVTE, there is a greater airflow resistance. And this greater airflow resistance usually creates an increased oral pressure. So we have a greater airflow resistance, and this in turn produces an increment in the oral pressure. So the increased resistance and the increased oral pressure in different degrees could be a good tool for voice training and voice therapy. Andrade in 2015, in this paper published in Journal of Voice, they measured or they reported, an increase in airflow resistance during tube phonation. And they reported also an increment of back pressure or oral pressure by increasing the tube length or by decreasing the tube diameter, or both at the same time, increasing tube length and decreasing tube diameter. Author also reported that relative changes in the diameter of straws affect oral pressure considerably more compared with the same amount of relative change in length. But when the tube is submerged in water, the depth of water is the most relevant variable affecting airflow resistance and, of course, oral pressure. In this study by McPhail et al. Published in 2014, they measure intraoral pressure produced by 13 SOVTE, and they reported that the highest values of oral pressure were found for WRT and for sternum straw phonation. On the other hand, the lowest values of oral pressure were reported for nasal consonant and for drinking straw phonation with the free end in air. Differences in oral pressure are possible associated to different degrees of airflow resistance produced by this SOVTE. So we know that this increment in the airflow resistance caused by SOVTE produce in turn a greater oral pressure, right? But this in turn creates a greater intraglottal pressure, which maybe is capable to produce a lower impact stress. Also, another consequence of this increment in oral pressure is an adaptation, is a compensation, which is a greater subglottic pressure. So in order to keep phonation, when we have an increment of oral pressure, we need to also increase subglottic pressure. And we have two options here. When the subglottic pressure increases, we can get a lower transglottal pressure or a higher transglottal pressure. When the subglottic pressure increment is greater than the oral pressure increment, we will get a higher transglottal pressure. But when the oral pressure increment is greater compared to the subglottic pressure increment, we will get a lower transglottal pressure. In this study by Radolf et al., an author measured the oral pressure and the subglottal pressure in several exercises using tube in air and tube into the water. And they reported that the higher the resistance, the degree of resistance caused by the exercise, the higher is the subglottic pressure and the oral pressure. Understanding that the subglottic pressure increment is a compensation, is an adaptation to the oral pressure increment. Very similar findings were reported by Guzman et al. In 2015, in a study entitled Air Pressure and Contact Quotient Measured during different SOVTE in subjects with different voice conditions. In this picture, in this figure, we have the baseline, where we can observe on the top, on the peak, the subglottic pressure, on the valley, the oral pressure, and the transglottal pressure, which is the difference between subglottic pressure and oral pressure. But what about when subjects were phonated in a drinking straw? So we can observe an increment of both oral pressure and subglottic pressure. This was for drinking straw. And we got an even higher increment of subglottic pressure and oral pressure when subjects were required to phonate using a stirring straw, which creates much more resistance compared to drinking straw. Similar results were observed with a silicone tube in air, and also similar results, but we got a greater increment of oral pressure and subglottic pressure when this silicone tube was submerged into the water. And also, we not only observe an increment in subglottic pressure and oral pressure, but also a nice oral pressure oscillation, which is attributed to the so-called massage-like sensation. So this massage-like effect of water resistance therapy, or WRT, is a great source of sensory stimulation necessary to change the voice production pattern, I mean the vocal demand response, and also to reduce the sensation of muscle tension, sensation of vocal fatigue, and throat discomfort in general. It is important to highlight that there are two main differences between tube in air and tube in water. The first one is the higher airflow resistance, and the second one is the water bubbling, which is attributed to produce the massage-like sensation. So bubbles create pulsating oral pressure measured between 15 and 40 Hz approximately, which are supposed to create a movement of laryngeal, pharyngeal, and oral tissues, creating the massage-like sensation, and also promoting a reduction of sensation of muscle tension and vocal fatigue. But let's take a look on the evidence related to the oscillation of oral pressure. We already mentioned that actually there is oscillation of oral pressure during WRT. In this study published in 2015, we reported that there is oscillation of oral pressure during WRT. There are also more studies reporting similar results, the presence of oscillation in oral pressure during WRT. But the next question is the oscillation of oral pressure during bubbling capable to move tissues? It is really capable to move tissues? So let's take a look on the evidence related to the movement of facial, laryngeal, and pharyngeal tissues. The main areas that supposedly oscillate during WRT are oral cavity, laryngeal area, and pharynx. Unfortunately, no published data we can find so far. A couple of years ago in Germany, at the University of Freiburg with Dr. Matthias Eckernach, we were performing a study to measure the possible oscillation of oral, laryngeal, and pharyngeal tissues during WRT using functional MRI. It seems, according to our observations, that oral pressure oscillation produces some oscillatory movement on tissues, in the laryngeal tissues, oral cavity tissues, and also pharynx tissues. In this new study, we are now analyzing the samples. We observe a possible oscillation of oral, pharyngeal, and laryngeal tissues during WRT and other double source of vibration SOVTE measured in this occasion with accelerometry. In this picture, you can see the experimental setup that we used. And let's take a look on these very nice pictures. On the top, we observe just the fundamental frequency oscillation, which is the baseline. But then, on the oral cavity, we not only observe the fundamental frequency oscillation, but also a modulation of the signal, which is supposed to be the oscillation of the oral cavity tissues. So we found that the oral pressure oscillation is really capable to produce oral cavity tissues oscillation. The same happened with the pharynx oscillation, with the pharyngeal tissues oscillation, and very similar result for laryngeal tissues oscillation. We also measure what happened with this tissue oscillation when using the Acapella device. The Acapella device is a vibratory PEP mucus clearance device, which is used for physiotherapists to remove the mucus from the airway. And we found a very similar result. You can observe that there is a modulation of the signal on the oral cavity tissues, also on the pharynx tissues, and also in the laryngeal area. We actually obtain more regular oscillation of the tissues and larger amplitude of oscillation with Acapella device compared to WRT. And our results are in line to the result by Sachente Kennedy et al. Published in 2019, where author reported a larger amplitude of vibration than water bubbling when performing phonation with Acapella, and also a more regular oscillation. We also analyze or observe a possible oscillation when producing other double source of vibration SOVTE, such as tongue trill, raspberry, and lip trill. And we found very similar results compared to Acapella device and WRT. Laukkanen in 2018 also reports some vocal fold secondary oscillation during babbling. But what about the evidence related to the massage-like sensation caused by babbling? There is only one published study, published in Journal of Voice in 2017, and the purpose of our study was to see the effect of double source of vibration semi-occluded vocal tract exercises on subjective and objective variables in subjects with voice complaints. We use objective variables and subjective variables. However, we found significant differences only in subjective variables. Both resonant voice self-perceived sensation and perception of muscle relaxation increased after 30 minutes of voice exercises and remain after 1 week of practice at home. A significant decrease in vocal tract discomfort scale score was also reported after 1 week of practice at home in this study. Of course, we need to control variables affecting babbling to get the best effect during WRT. There are at least 3 main physical variables that we need to take into account when performing WRT. The first one is babbling frequency. The second one is babbling amplitude, and then babbling regularity. Why are they so important? Because they could impact on the oral pressure oscillation, and of course they could impact in the massage-like effect felt by patient, which in turn could affect the vocal demand response and vocal effort, affecting in long and short term the performance and perceptual aspect of vocal fatigue. In a monitoring study by Visvaka in 2017, authors suggested that airflow rate, tube diameter, and vocal tract volume are independent variables affecting physical features of babbling mentioned before. In a study which is in press right now in Journal of Voice, we try to answer the following question. How do tube diameter and vocal tract configuration affect oral pressure oscillation characteristics caused by babbling during WRT? So patient subjects were required to phonate in 3 different diameter tubes, 2 centimeter, 1 centimeter, and 0.5 centimeter diameter tubes. They also were required to phonate using 2 vocal tract configurations, horizontal position and vertical position, in order to increase the total volume of the vocal tract. So we usually have a smaller volume of the vocal tract with the horizontal position, which is the regular vocal tract position, and we can get a greater vocal tract volume, total volume, when we are performing this kind of exercises using a vertical position. Participants were required to self-assess their massage-like sensation. We also included as an outcome air pressure-related variables, such as oral pressure oscillation frequency, oral pressure oscillation amplitude, oscillation jitter, and oscillation shimmer. The two last variables are related to the bubbling regularity. We found that inner diameter of tube and configuration of the vocal tract affect bubble characteristic and massage-like sensation during WRT. Specifically, larger tube diameters and vocal tract volumes seems to produce more regular bubbles, lower bubble frequency, and larger bubble amplitude, causing a more evident massage-like sensation. Therefore, control of these variables is apparently relevant to obtain the best effect in patients with voice complaints. The vocal tract inertance can affect the voice source function in two ways, as you may know. The first one is the acoustic aerodynamic interaction, and the second one is the mechanoacoustic interactions. The acoustic aerodynamic interactions, the shape of the vocal flow or the glottal flow pulse is affected by the acoustic pressures in the vocal tract, creating an increased acoustic energy in high spectral region, and also a brighter and louder sound. On the other hand, the mechanoacoustic interaction create an increased vocal tract inertance that affect the vocal fold vibration by itself, lowering the phonation threshold pressure, which, as you may know, is related to the phonatory effort, creating an easy of phonation. And in some report, there are also data supporting that there is a decrease in the perceived phonatory effort. Both interactions, the acoustic aerodynamic interaction and the mechanoacoustic interactions together could positively impact in producing an increment of the vocal economy because of the brighter and louder sound and the decrease in the perceived phonatory effort. So the acoustic and acoustic aerodynamic interaction and the mechanoacoustic interaction could produce, as I mentioned before, an increment of vocal economy, which in turn could positively impact creating a healthy vocal demand response and a lower vocal effort, affecting in long and short term the performance and perceptual aspect of vocal fatigue. Related to the first interaction and regarding the spectral energy distribution as an SOVTE, we have performed at least 3 studies in order to assess the possible changes on spectral energy distribution after tube phonation. In general, we have reported an increment of the energy in the highest region of the spectrum, creating a less steep spectral tilt. Very similar results were found in this study, where we reported more energy in the higher spectral region and a less steep spectral tilt. What about the relationship between phonation threshold pressure and SOVTE? As you know, a low PTP is also associated with a proper vocal demand response, and it is an objective variable indicating a reduction of vocal effort. In this study performed by Conroy et al. And published in Journal of Voice in 2014, author reported a decrease on PTP with tube and other vocal tract constrictions. And a very similar or comparable result were reported when using the semi-occluded face mask phonation therapy compared to tube phonation. In a recent study published in Journal of Voice in 2019, we assessed the immediate effect of the semi-occluded ventilation mask in subjects with functional dysphonia and subjects with normal voice. We found that the PTP showed a significant decrease after SOVM exercises in both experimental groups, dysphonics and normal voice. Similar results were obtained for subglottic pressure. We also reported a decrease for dysphonic subject with mask and normal subject with mask. The self-perceived resonant voice quality show also a significant increase after SOVM exercises in both experimental groups, dysphonics and normal voice subject. SOVTE and the degree of vocal fold aduction is another very relevant aspect for vocal demand, response, and vocal effort, because this feature, the vocal aduction, could impact on the vocal economy. And this in turn could cause a change in the performance and the perceptual aspects of vocal hygiene, vocal fatigue, There are some studies trying to establish a relationship between different SOVT and the degree of vocal fold aduction. Some of them have reported a decrease in vocal fold aduction during or after SOVT exercises, and others have reported an increase of vocal fold aduction during or after exercises. We have at least 5 studies where we tried to measure the vocal fold aduction during different SOVT using a different assessment method, electrocardiogram, high-speed digital imaging, and others. Overall conclusions. We have reported in these studies that vocal fold aduction increases with the degree of airflow resistance created by some SOVT. In general, narrower tubes tend to produce higher vocal fold aduction, and deeper immersion of tube in water produce a higher vocal fold aduction compared to shallower immersion. Also, it is important that low flow resistant exercises, such as wide tube in air, nasal consonants, and trills, tend to reduce vocal fold aduction. Control of vocal fold aduction by using different SOVT is another relevant aspect to modify vocal demand response and vocal effort. There is also a possible relationship between SOVT and vocal tract configuration. In the 3 studies, we tried to observe to measure the possible changes on vocal tract configuration caused by different SOVT. We have used different assessment methods, and in general, we have reported that a lower vertical laryngeal position, a wider pharynx, higher velum, and a narrower epilaryngeal tube is obtained during tube phonation. Even though these changes have been observed mainly during tube phonation and not always remain after tube phonation, they are still very important changes because they can contribute with a proper sensory stimulation input during exercises to build an appropriate motor pattern, which is the output that we want to create or we want to modify, decreasing maybe the vocal fatigue in both performance and perceptual aspects. There is also some reports, some mainly clinical reports, associating an improved breathing management with some SOVT. So SOVT are supposed to activate glottal and breathing function. As I mentioned at the beginning of this presentation, there is not only one feedback from the filter to the source, but also we can find a second feedback to the filter to the breathing function. So the increased resistance in different degree because of the SOVT, as I mentioned before, produce an increased oral pressure, which also produce an increased subglottic pressure as a compensatory behavior. And this subglottic pressure is possible create a greater and a better control muscle expiratory activation. As I mentioned before, please recall that we have not only one feedback from the filter, but we can have also a secondary feedback from the filter to the breathing function. So Also, I would like to mention that we have performed at least 4 randomized control trials exploring the effectiveness of 4 different voice therapy protocols based on SOVTE. One of them is published, just one of them. The first study, which title is Efficacy of Water-Resistant Therapy in Subjects Diagnosed with Behavioral Dysphonia, a randomized control trial. We had 2 groups, the experimental group performing WRT and the control group performing tube inert. In the second study, physiologic voice rehabilitation based on WRT therapy with connected speech in subject with voice complaint. We had also 2 groups. In the experimental group, subject doing phonation using the pocket box and mask box, which are commercial voice devices, plus vocal hygiene, and the control group only vocal hygiene. In the third study, a voice rehabilitation protocol with semi-occluded ventilation mask in subject with vocal fatigue and vocal effort, we included 2 groups, an experimental group with subject phonated with a semi-occluded ventilation mask plus vocal hygiene, and a control group only with vocal hygiene. And finally, the fourth study, effectiveness of a physiologic voice therapy program based on different semi-occluded vocal tract exercises in subject with behavioral dysphonia, a randomized control trial. We had also 2 groups, the experimental group phonating using various SOVTE plus vocal hygiene, and a control group with vocal hygiene only. So it is important to highlight that these 4 studies were long-term studies. I mean, we measured pre and post, and the post was measured several voice therapy sessions compared to the pre-condition. So we have no time, unfortunately, to talk about in detail about the result. But in general, results from the 4 studies have shown that there is a decreased phonation threshold pressure after several sessions of voice therapy using different protocols, including SOVTE. We have found also a decreased subglottic pressure in some of them, a decreased voice handicap index score, a decreased perceived phonatory effort, an increased self-perceived resonant voice quality, and also a decrease in the vocal tract discomfort scale score. Probably, all these changes are capable to promote an improved vocal demand response, meaning an improved voice production in response to the perception of a communication scenario. Probably these changes are also capable to produce a decrease in the vocal effort, meaning a decreased exertion to the perceived communication scenario, and more importantly, a decrease in vocal fatigue, meaning less decline in vocal function, considering both performance and perceptual aspects. Thank you very much.